The first clue. Attempts to read the mystery story are as old as human thought itself, only a little over 300 years ago. However, did scientists begin to understand the language of the story. Since that time, the age of Galileo and Newton, the reading has proceeded rapidly. Techniques of investigation, systematic methods of finding and following clues have been developed. Some of the riddles of nature have been solved, although many of these solutions have proved temporary and superficial in the light of further research. A most fundamental problem for thousands of years, wholly obscured by its complications, is that of motion. All those motions we observe in nature, that of a stone thrown into the air, a ship sailing the sea, a cart pushed along the street, are in reality very intricate. To understand these phenomena, it is wise to begin with the simplest possible cases and proceed gradually to the more complicated ones. Consider a body at rest, where there is no motion at all. To change the position of such a body, it is necessary to exert some influence upon it, to push it or lift it, or let other bodies such as horses or steam engines act upon it. Our intuitive idea is that motion is connected with the acts of pushing, lifting or pulling. Repeated experience would make us risk the further statement that we must push harder if we wish to move the body faster. It seems natural to conclude that the stronger the action exerted on a body, the greater will be its speed. A 4-horse carriage goes faster than a carriage drawn by only 2 horses. Intuition thus tells us that speed is essentially connected with action. It is a familiar fact to readers of defective fiction that a false clue muddles the story and postpones the solutions. The method of reasoning dictated by intuition was wrong and led to false ideas of motion which were held for centuries. Aristotle's great authority throughout Europe was perhaps the chief reason for the long belief in this intuitive idea. We read in the Mechanics for 2000 years attributed to him. The moving body comes to a standstill when the force which pushes it along can no longer so act as to push it. The discovery and use of scientific reasoning by Galileo was one of the most important achievements in the history of human thought and marks the real beginning of physics. This discovery taught us that intuitive conclusions based on immediate observation are not always to be trusted, for they sometimes lead to the wrong clues. But where does intuition go wrong? Can it possibly be wrong to say that a carriage drawn by 4 horses must travel faster than one drawn by only 2? Let us examine the fundamental facts of motion more closely, starting with simple everyday experiences familiar to mankind since the beginning of civilization and gained in the hard struggle for existence. Suppose that someone going along a level road with a pushcart suddenly stops pushing. The cart will go on moving for a short distance before coming to rest. We ask, how is it possible to increase this distance? There are various ways, such as oiling the wheels and making the road very smooth. The more easily the wheel turn and the smoother the road, the longer the cart will go on moving. And just what has been done by oiling and smoothing? Only this. The external influences have been made smaller. The effect of what is called friction has been diminished, both in the wheels and between the wheels and the road. This is already a theoretical interpretation of the observable evidence, an interpretation which is in fact arbitrary. One significant step farther, and we shall have the right clue. Imagine a road perfectly smooth and wheels with no friction at all. Then there would be nothing to stop the cart, so that it would run forever. This conclusion is reached only by thinking of an idealized experiment, which can never be actually performed. Since it is impossible to eliminate all external influences, the idealized experiment shows the clue which really formed the foundation of the mechanics of motion. Comparing the two methods of approaching the problem, we can say the intuitive idea is the greater the action, the greater the velocity. Thus, the velocity shows whether or not external forces are acting on a body. The new clue found by Galileo is, if a body is neither pushed, pulled, nor acted on in any other way, or more briefly, if no external forces act on a body, it moves uniformly, that is always with the same velocity along a straight line. Thus, the velocity does not show whether or not external forces are acting on a body. Galileo's conclusion, the correct one, was formulated a generation later by Newton as the law of inertia. It is usually the first thing about physics which we learn by heart in school, and some of us may remember it. Every body preserves in its state of rest or of uniform motion in a right lane unless it is compelled to change that state by forces impressed thereon. We have seen that this law of inertia cannot be divided directly from experiment, but only by speculative thinking consistent with observation. The idealized experiment can never be actually performed, although it leads to a profound understanding of real experiments. From the variety of complex motions in the world around us, we choose as our first example uniform motion. This is the simplest because there are no external forces acting. Uniform motion can, however, never be realized. A stone thrown from a tower, a cart pushed along a road can never move absolutely uniformly, because we cannot eliminate the influence of external forces. In a good mystery story, the most obvious clues often lead to the wrong suspects. In our attempts to understand the law of nature, we found similarly that the most obvious intuitive explanation is often the wrong one. Human thought creates an ever-changing picture of the universe. Galileo's contribution was to destroy the intuitive view and replace it by a new one. This is the significance of Galileo's discovery. But a further question concerning motion arises immediately. If the velocity is no indication of the external forces acting on a body, what is? The answer to this fundamental question was found by Galileo, and still more concisely by Newton, and forms a further clue in our investigation. To find the correct answer, we must think a little more deeply about the cart on a perfectly smooth road. In our idealized experiment, the uniformity of the motion was due to the absence of all external forces. Let us now imagine that the uniformly moving cart is given a push in the direction of the motion. What happens now? Obviously, its speed is increased. Just as obviously, a push in the direction opposite to that of the motion would decrease the speed. In the first case, the cart is accelerated by the push. In the second case, decelerated or slowed down. A conclusion follows at once. The action of an external force changes the velocity. Thus not the velocity itself, but its change is a consequence of pushing or pulling. Such a force either increases or decreases the velocity, according to whether it acts in the direction of motion or in the opposite direction. Galileo saw this clearly and wrote in his two new sciences. Any velocity once imparted to a moving body will be rigidly maintained as long as the external causes of acceleration or retardation are removed, a condition which is found only on horizontal planes, for in the case of planes which slope downwards, there is already present a cause of acceleration, while on planes sloping upwards, there is retardation. From this it follows that motion along a horizontal plane is perpetual, for if the velocity be uniform, it cannot be diminished or slackened, much less destroyed. By following the right clue, we achieve a deeper understanding of the problem of motion, the connection between force and the change of velocity, and not as we should think according to our intuition. The connection between force and the velocity itself is the basis of classical mechanics as formulated by Newton. We have been making use of two concepts which play principal roles in classical mechanics, force and change of velocity. In the further development of science, both of these concepts are extended and generalized. They must therefore be examined more closely. What is force? Intuitively we feel what is meant by this term. The concept arose from the effort of pushing, throwing, or pulling, from the muscular sensation accompanying each of these acts, but its generalization goes far beyond these simple examples. We can think of force even without picturing a horse pulling a carriage. We speak of the force of attraction between the sun and the earth and the moon, and of those forces which cause the tides. We speak of the force by which the earth compels ourselves and all the objects about us to remain within its sphere of influence, and of the force with which the wind makes wave on the sea or moves the leaves of trees when and where we observe a change in velocity. An external force in the general sense must be held responsible. Newton wrote in his Principia, an impressed force is an action exerted upon a body in order to change its state, either of rest or of moving uniformly forward in a right line. This force consists in the action only, and remains no longer in the body when the action is over. For a body maintains every new state it acquires by its vis inertia only. Impressed forces are of different origins, as from percussion, from pressure, from centripetal force. If a stone is dropped from the top of the tower, its motion is by no means uniform. The velocity increases as the stone falls. We conclude an external force is acting in the direction of the motion, or in other words, the earth attracts the stone. Let us take another example. What happens when a stone is thrown straight upward? The velocity decreases until the stone reaches its highest point. and begins to fall. This decrease in velocity is caused by the same force as the acceleration of a falling body. In one case, the force acts in the direction of the motion, in the other case, in the opposite direction. The force is the same, but it causes acceleration or deceleration according to whether the stone is dropped or thrown upward.